Okay, so I'm going to start with cell chemistry today, and this is not serious organic or inorganic chemistry. It's just very basic chemistry that we are going to do in this class. Okay, so don't tie yourself into knots over too much of this. Okay, it's quite simple if you kind of study it in packets. So let's look at matter and energy. Matter is something that you can touch and feel. So that's why we say it's tangible. Okay, you can touch and feel. So it's present in a liquid form like water. It's liquid. In a gaseous state, carbon dioxide, you can smell it. Okay, you can smell the air around you. Or it could be solid, like something like this, like a table. So this is solid. So this is what matter is. When you compare that with energy, energy is not tangible. You cannot touch or feel it. But it is something, we say it's the capacity to do work. And, just think of it in everyday life. I don't have much energy. What you're trying to say, I just don't have that in me to do this much work. Or I just feel like I have a lot of energy. So it's really your capacity to do work. Okay? And it actually is what sets matter in motion. So that's how we kind of look at energy. Now, energy is of two types. One is called kinetic energy, which is action energy, when something is being done. The other one is potential energy, which is stored energy. That is, you have the capacity to do that kind of work, but at that point in time, you are not. And to give you an example, the unused batteries that you have in a device which you're not using, the batteries that are put inside a device which you're not using, that's potential energy. Because it has the capacity to do work. When you turn on that device, then those batteries kind of give the power for that device, and so that potential becomes kinetic energy. Okay? So in your body too, anything which is stored, for example, to be used later on, that is potential energy, and when you're actually doing the work, then that is kinetic energy. Now let's look at the forms of energy. So these are the four different forms. Chemical energy is the type which a lot of processes in our body utilize, where bonds are made or broken, and ATP is either used up or stored, and this is its most useful form. ATP stands for, does anybody know? Okay, it's adenosine triphosphate. Next is electrical energy, where charged particles move about, and these charged particles in our body are ions. In your home, the electrical wiring that is present, that is electrical energy, how the impulses travel through that. In our body, it is used by the nervous system and the muscular system. So when electrical impulses pass through the nervous system, land on a muscle, and the muscle contracts, that is electrical energy. Okay? Mechanical energy is a direct movement of matter. For example, if I push a table or a chair, that's mechanical energy in your body. If you kind of lift up something like this, okay, you're pushing something with your hand, dumbbells, that's mechanical energy. And lastly, we have electromagnetic energy, which is also known as radiant energy, where it moves in waves like ultraviolet light, X-rays, infrared. All of these are electromagnetic kind of energy. When the light waves hit your retina, for example, and then you're able to see. So what happens is when it strikes the retina, the cells over there, they are stimulated, an electrical impulse passes, and then you're able to visualize whatever it is that you're seeing. So here you can see the light energy got converted into electrical energy. Okay? So that means energy can be converted from one form to another. Another example is when ultraviolet light hits your skin, then under the skin there's an inactive form of vitamin D, which is converted into the activated form of vitamin D. That's why they tell you go out in the sun and get exposed to ultraviolet light, though not too much, right? So here you can see that activation is a chemical type of energy, and ultraviolet light striking, so you can see this radiant energy is converted into chemical energy. Okay, so you can see how there's an energy conversion. Another example in your house is just that you turn, let's say you have a fan and you plug it into a socket and you turn on the socket, it's electrical energy, and then the blades of the fan move, so you can see how electrical energy is converted into mechanical energy. So you see that? So they're different, all over in your body and outside. You can see that there are various examples that you can find how energy is converted. Now here, let's answer this question, that having discussed kinetic and potential, which of the following is an example of conversion of potential energy into kinetic energy? So here are your choices. As you can see, when you're synthesizing, that means you're making ATP from glucose, or when you're breaking down ATP. ATP is a stored molecule. When you break it down to drive muscle contraction, or when you pump ions across a cell membrane, or example, you've eaten some chicken and then the protein is getting digested in your stomach. So choose which one of these do you think is okay, very good. 62% got it right. Let's see why that's the right answer and why the other ones are not. Synthesis of ATP from glucose. See, work is being done. It's not that something was stored and then that was then brought about and asked to be converted from potential to kinetic. In this, it's kinetic energy all the way through. You're synthesizing something. It's like, remember I said pushing something like this. You're synthesizing, you're doing work all the time. So this is an example of kinetic energy. Pumping ions across a cell membrane. Again, the same thing. Work is being done at this time. It isn't as if something was stored and now you're calling upon it to change from potential to kinetic. Okay? So pumping ions across a cell membrane or even digestion of protein in the stomach work is being done. Right? So this is all, the first and the lower two are examples of kinetic. ATP, and I gave you the example, ATP is a stored molecule. So it's like your battery which you're storing inside. So it's a stored energy molecule which is kept inside, and then when the body needs it, then it is used. So it's hydrolysis is when ATP is now broken down and muscle contraction is brought about. So that is the example of a conversion of potential into kinetic energy. Okay? Now let's look at how we break down matter into further subdivisions. So matter is broken down into elements, which are simple forms of matter, and there are about 118 of these. 92 occur in nature. The four main elements which are seen in our body. Can anyone help me out? Which ones are these? No. Oh, you wish gold. Did someone say nitrogen? Okay, yes, nitrogen, yes. So hydrogen, oxygen, carbon, and nitrogen are the four main ones which are seen in our body, and the others are present as trace elements. Here are some names that we have. Whenever we talk about elements, especially in chemistry, we always use some scientific names for them. And these are known as their scientific symbols or scientific names. They are either the first letter of their name, or they may be the first and second, or you might use a Latin name for that. So hydrogen, for example, H, the first letter. Oxygen is O, the first letter. C is for carbon, again the first letter. Au is for gold. Gold comes from the Latin name aurum. Gold is from aurum. Silver, the name for silver is argentum. Zinc, Z and N. Magnesium, M and G. Sodium, another Na. You would think sodium should have been with an S. It comes from, again, the Latin name natrium. Copper, Cu, comes from cuprium. So that's how you have Cu. So you can see sometimes you may not necessarily have the first and second. If, the second one is used up for something else, then you can't use that for this. So for example, Mg, magnesium, you can see that, the G comes after the A. So you can't use that because it's already been taken up by something else. Now, elements too are broken into smaller particles which are known as atoms. And these atoms have physical and chemical properties which actually are the properties of that element. The physical properties are ones that you can sort of smell or sense or touch, like texture, you can smell it. And the chemical properties are ones which show how they interact with other atoms. So when you look at an atom and you kind of break it down, you obviously cannot look at it under a microscope, so this has to be done in, using special equipment. But when you break it down, you will notice that the atom has a central area which is known as the nucleus, which is the heaviest part of the atom. And then on the periphery, there's kind of a cloud-like zone, which is known as the electron cloud, and it's kind of got little orbits around which these tiny particles, which are not that heavy, they kind of dance around or circulate around. So these are known as electrons, which are the tiny particles which are surrounding the nucleus. They travel in what are called orbitals. It's like an orbit. They go around the nucleus. They are of very low matter or low mass. They don't have too much weight. These are negatively charged particles, electrons. In the nucleus, you have the heavy particles. So this is the dense zone of the atom. Here you have protons, which are with a P. Protons are positively charged particles, heavy. And along with protons in the nucleus, you also have neutrons, which are neutral. That's why they're called neutron. They don't have any charge, so they are also heavy. So that's why they're right in the center. Every atom has to have at least one proton. Every atom has to have at least one proton. So hydrogen is one perfect example. It has one proton. And an atom is what is said to be electrically neutral. That means its positive and negative charges are the same. So if you know the number of protons, would you know the number of electrons? Yes, right? You would know the number of electrons, because if it's electrically neutral, if you have 4 protons, you have to have 4 new electrons because they have to cancel each other out, right? The charges have to cancel each other out. Now we have some terms that we use. Atomic number is the number of protons that an element or an atom has, and is written at the lower left-hand corner here. So for example, helium, its atomic number is 2, so it has 2 protons. Mass number is a term which is used. So atomic number is equal to the number of protons. Mass number is equal to the number of protons plus neutrons. So again, with helium, the mass number is 4 and it's written in the upper left-hand corner. That means it has 2 protons and 2 neutrons. Now there's another term which is called atomic weight. Now when we look at these elements, we sometimes have different forms of an element. For hydrogen, for example, it has 3 forms of it. And let me first ask you these questions, and then we'll come to I'll go back to this atomic weight. So let's see, what is the charge of the nucleus? So think of what is present in the nucleus and tell me what is the charge of the nucleus. Okay, the charge of the nucleus is positive. Remember, what is there in the nucleus? Protons and neutrons. Protons are positive, neutrons are neutral, so they don't, no charge. So it's positively charged, right? The nucleus is positively charged. What is the overall charge of an atom? Which is what some of you might have been thinking when I asked that question. What is the overall charge of an atom? Yes, the overall charge is neutral because the protons and electrons, the electrons being negative, they are equal in number. So the overall charge of an atom is neutral. Whereas the nucleus, which has only protons, the nucleus is positively charged. Okay? Okay, let's see this kind of question that you might get. The lithium has 3 protons and 4 neutrons in its nucleus. So what is its mass number? Remember, atomic number or mass number. Seven. Yes, very good. The mass number is the sum of the protons and neutrons. So 4 plus 3 is 7. So how about this one? Sodium has 11 protons and 12 neutrons. So how many electrons will sodium have? $11. Very good. That's the correct answer. Look at this. I said the number of protons, first of all, if it's electrically neutral, so the number of protons and number of electrons will be the same. So if you know that it has 11 protons, don't get thrown off by any other numbers that get put into the equation, okay? So 11 protons means in order to be electrically neutral, it has to have 11 electrons, okay? So you might get the question worded differently. The atomic number of an element is 11. How many new electrons does it have? So then you start thinking the atomic number means the number of protons. So it has got 11 protons. So that means it will have 11 electrons. Okay? Yes?
The number of protons is always going to be the same as the number of electrons.
Yes.
Always.
Because an atom is electrically neutral. Yes. Yeah. So this is just a review, quick review for you guys to kind of look at home, which tells you some of these things that we just went over. The nucleus is positively charged, and I told you hydrogen is has one atom. Is the simplest atom. It has just one proton and hence one electron. It is one of those atoms which has no neutrons, hydrogen. Okay? Now I was talking about, yes. I'm coming to that. Yeah, I kind of said, I was discussing atomic weight, and I was talking about hydrogen, and I said, okay, let me first ask you these questions before I go on to this subject. So we said hydrogen, the most prevalent form of hydrogen is this one, where it has one proton and one electron. There are no neutrons in the nucleus over here, okay? Now, hydrogen has other forms also. So when you have different forms of an element, we call that an isotope. So the two other forms of hydrogen are where the proton number is the same, but it is only that they differ in the number of neutrons that they have. So in the second type of hydrogen that we find, this which is not called hydrogen, it is called deuterium. This has one proton and one neutron, and 1 electron. And this one, which is tritium, you have 1 proton, 2 neutrons, and 1 electron. So if you look at them, you can see that the proton number remains the same. Obviously, the electron number will also remain the same. It's only the neutrons which vary. So either you have none, or you have 1, or you have 2. You see that? So these are called isotopes, where the number of neutrons varies between the different forms of that atom or its element. And then how do you calculate the atomic weight? The atomic weight then is the average of all the isotopes put together. So if you take the average of all these three and put together, that is the atomic weight, because we never count the electrons in the weight, because electrons have a very negligible mass. So atomic weight is the average of all the isotopes which occur in nature of that element. It also so happens that as a general rule, we often take it to be the atomic weight is often taken to be the mass number of the most prevalent atom that is occurring, most prevalent isotope that is occurring. So for example, in these three forms, the most prevalent isotope which occurs is hydrogen. Deuterium and tritium do not occur as often in nature as hydrogen. So when you take the atomic weight, we say it is almost equal to the atomic or the mass number. Have you followed what I'm saying?
I still don't understand why hydrogen is an isotope.
No, it's not why it is an isotope. Isotope is just these are different forms of an element. For example, like a color, like say you take orange. So you have orange, you have burnt sienna, and you have maybe peach. They're all same shades. Similarly, if you think of it like that, isotopes are just different forms of an element. So you have they all have some common properties, one of which is they will all have the same number of protons and the same number of electrons, but they'll only differ in the number of neutrons that they have. So we have hydrogen, we have deuterium, we have tritium. We say that these are isotopes. Got that? And then when we talk about atomic weight, the first thing is that atomic weight by definition is the average of all the isotopes, the average mass of all the isotopes which are seen in nature. And then we also kind of make a further caveat to that, saying that the atomic weight is usually the weight of the most common isotopes, the mass number of the most common isotope. In the case if we were taking hydrogen isotopes, we would take the first one, which is hydrogen. Got that? Okay. So atomic weight is it's the same as mass number, but only difference being we take the average of the isotopes. So if this one was 1, this one was 2, and this one was 3, then you take the average, 3 plus 2 plus 1, right? And so that would be 6. And the average of that is what? 2, isn't it? But the most frequently occurring isotope is hydrogen. So the mass number, instead of saying it as 2, we say it's 1.0008 or something like that. You see that? So it's the most frequently occurring or most prevalent isotope. Got that? Now, there are certain isotopes which are present in nature which tend to spontaneously decay, and we make use of that. So when they spontaneously decay, examples are iodine, cobalt is another one. They give off radioactivity, and we can actually use that radioactivity by special scanners and so on, and we use it in medical diagnostics. We also use it for radiation treatment. So in cancers, when you give anybody radiation treatment, you often use cobalt, or you also use radioisotopes to diagnose certain conditions. For example, thyroid cancers. So we push radioactive iodine into the body. It goes and gets lodged because the thyroid gland tends to take up iodine very rapidly. And then we can sort of run a scan in that area, and wherever we find that there is more activity, then we suspect that maybe there's a problem over there. So we kind of use this feature of being able to spontaneously combust or decay and give off radioactivity. We use it in medical diagnostics. Okay?
So they go in the body, and when they're decaying, that's when you're looking at
the radioactivity. Yes.
Yeah.
Yes.
Okay.
Yeah.
So it's often like getting bigger. It's
No. Yes.
Okay.
Yeah. Now let's look at these two terms called molecules and compounds. Atoms are never present singly in nature. They always combine with each other. So when atoms of the same kind combine together, they form a molecule of that element. So for example here, two atoms of oxygen have combined to form a molecule of oxygen. So we write it as O2 to show you that two atoms have combined. When atoms of different elements combine together, firstly they form a compound and they form a molecule of that compound. So again, I'll repeat. A molecule is when atoms combine together.
Similar atoms, right?
When similar atoms, not always. A molecule is when atoms combine together. When similar atoms combine together, they form a molecule of an element, like oxygen, hydrogen, nitrogen. When atoms of different, nitrogen atoms will combine together, they'll form a nitrogen molecule. When hydrogen atoms will combine together, they'll form a hydrogen molecule. When oxygen atoms combine together, they form an oxygen molecule. What is oxygen? An element, right? When different atoms combine together, they'll form a molecule, but at this time you do not call it the molecule of an element, you call it a molecule of a compound. If you think of what is a compound is complex. It has different elements in it, okay? So if you look at this CO2, carbon dioxide, it has carbon plus oxygen in it. So there are two elements. So you can see it forms a compound. So a compound is something which has two or more elements. Hence, it will be made up of atoms of different elements. So let's look at some more compounds here. Sodium sulfate, sodium, sulfur and oxygen. Calcium chloride, calcium and chlorine. So these are compounds. So up here, if you look at this, Au, gold, is this an element or a compound? Sodium, element or compound? Water, compound or element? Copper sulfate, compound. So you got that, right? Okay. Let's look at this one. How many elements are present in sodium hydrogen sulfate?
Can you say it again?
Sodium hydrogen sulfate. Okay, 4. There are 4. And let's see. Sodium, one element. Hydrogen, another element. Sulfur, S, another element. O, oxygen, another element. So 4. Okay? So sodium, hydrogen, sulfur and oxygen. 4 elements. Okay, now let's see, we were talking about atoms and we were talking about electrons and then, their properties. So let's see how these atoms actually combine with each other. So they combine by forming bonds between them. The bonds are formed differently and these are known as chemical bonds. Now there are certain elements in nature which do not combine with anything. They don't react. They're kind of just by themselves. So let's put them as being very introspective. They don't like to combine with anyone. We call them inert elements. Examples of inert elements are they're called noble gases. These are helium and neon. And you'll see why they are inert in a few minutes. Most other elements are reactive elements. So we call them active elements. They're chemically reactive or chemically active elements. And the reason they are able to react with other elements is because, if you remember, we talked about electrons and protons. The electrons surrounded the nucleus. They were present, sort of going around the nucleus in an orbit. We call them orbitals. you know. So you have different kind of shells or different orbitals around the nucleus. And it's kind of a unwritten, or it's a rule in chemistry, that the first orbital around the nucleus has the capability of containing a maximum of 2 electrons. Then the next orbital, the second orbital, has a capability of containing 8 electrons maximum. So let's say the first orbital can have a maximum of 2 electrons. The second one, after the first 2 have filled the first orbital, then they go into the next, you have the capability of having a maximum of 8 electrons. The third orbital has a capability of 18 electrons, and so on. You know, as the number of electrons in any element increases, the number of orbitals will also increase, and the number of electrons in each orbital will also increase. Okay?
Does it increase by a particular
number? No. So now you have a rule which is known as the octet rule. So every atom tries to make sure, in order to become stable, it wants to make sure that in its outermost shell it has 8 electrons or 2. So the octet rule, octet is 8. So the octet rule is that every atom, in order to become stable, wants to make sure that in its outermost cell, somehow it either will get or it will throw off some electrons. It has those 8 electrons, okay? Or, as I'm saying, even 2 is allowed. So if there is an atom which has only 1 orbit and it's got just 2 electrons, it's okay. So it either tries to get the 2 or it tries to get 8. Got that? So that's why, can you see that helium and neon are inert? Because look at helium, it's got 2. And look at neon, it's got 2 in the first and it's got 8 in the other one, in the second orbital. So it's achieved its stability. So that's why now it doesn't react with anything. So that's why these are called inert. Okay?
So they're basically set.
They are set. They don't want anything from anybody. That's right. Yes. Whereas these guys, look at these. For example, hydrogen has only 1 electron. So it wants 1 more. So one hydrogen atom can react with another hydrogen atom. They can both share that 1 electron, which we'll see in the type of bonding. So they'll both have 2. Here we have carbon has 4, right? It either has to give away 4 or to get 4. Because if it gets 4, then it will have 8. It gives away 4, then it will have 2. Remember, it has to get either 2 or 8. Got that?
So it can't have 2 in the outer...
No. In the first orbit, if there's only 1 orbital, then it can have 2. But otherwise, whatever others there are, only 8 is allowed in order for it to be stable.
So it has to give away 4 or get 4.
Get 4, yes. Yes. Okay? So this outermost shell of the electron, of the atom, where the reaction can occur, that is known as the valence shell. So the outermost shell of an atom, where the electrons are capable of reacting, that is known as the valence shell. For example, in this would be the valence shell. In this one, this would be the valence shell. In this one, this would be the valence shell. Can you see this? In this one, this is 2, this is 8, so these won't react. This one is the valence shell because it's got 1, so it wants to throw off that 1. It's easier to throw away 1 than to get 7, right? So this is the valence shell. In this one, this is set, this is stable, this is the one which needs to either get 4 or give away 4, so that's the valence shell, okay? So let's now look at the type of bonds that are happening. So as I said, we can either give away or share. Yes. Oh, 18 was that in the third shell you can have a maximum of 18. But in order to become stable, you're only allowed 8 are the only ones which are allowed to interact. So in order for what it will have to do, if you have 18, you have to give away 10. You see that? Okay. So here, remember I said you can either give away or you can take or you can share. So when you're giving or taking from someone, that kind of a bond which is formed is known as an ionic bond. These are weak bonds. We call them weak because they're not attracted very strongly. They can break. They don't need too much energy to break them. And let's take an example here. You all know common salt, sodium chloride, and how exactly is sodium chloride formed. So if you look at sodium and you count the number of electrons, so there are 2 in the first orbital and there are 2, 4, 6, 8 in the second one. So 8 and 2, 10, and 1 in the third orbital. So it has a total of 11 electrons, right? And look at chlorine. So it has 2 and then it has 8, so 10, and then it has 7 in the outer one. So this is 17. So now if sodium were to give 1 electron to chlorine, what would happen? Then now its orbital would have 8 and it would be stable. And if chlorine were to get that 1, it would have 8 in its third orbital. It would become stable. Do you see that? So this one gives 1 and this one receives 1. So you get sodium chloride formed, and the bond between them is known as an ionic bond.
Is there restrictions to how many orbitals?
No.
So they can have 5, 6.
Yes.
But
8 is the maximum reactive number of electrons, yes. So now here, when sodium gives away 1, what happens? It's losing 1 electron, right? So it's lost 1 negative charge. So it becomes positively charged. And when it becomes positively charged, we call it a cation. The way you'll remember cat, this plus sign. So sodium, can you see, has this positive sign? Because remember, it had the total number of protons and electrons to begin with are always the same, right? Now, if it gives away that 1 electron, it will have less electrons, right? The protons will be more, so it will be positively charged. Chloride, which receives that extra electron, has now a greater negative charge, so it is negatively charged and it's known as an anion.
So it's got protons in.
Yes, but remember, these are not simple, they are not existing separately, they are combined here. Okay, they are combined here, they are forming a bond.
So in these it's possible to have different electrons.
Yes, when the bond is being formed, that's how the bond is formed, because it gives 1 and it receives 1, but they are attached to each other, so they're not separate. When they were separate as atoms, as they were sodium atoms, then they are stable. But here now a new substance has been found, a compound has been formed, which is sodium chloride, whose properties are totally different from sodium and chlorine. Okay? Now these ions which are formed, cations and anions, these are very, very important because in your body it's the ions which actually move across cell membranes. They allow water to go towards an area of higher concentration. So they have a lot of properties. So let's look at the one property which is known as tonicity. So ions are also known as electrolytes because they have charges. They are called electrolytes because they can conduct electricity. And when you take a solution, and let's say take this solution of 50 ml of just water. So this is 100% water. So we'll say 100% concentration of water. Now let's take this solution here where you took 50% of 50 ml of water and you put 25 grams of sodium chloride in it. That sodium and chloride will actually break up into the ions, so sodium with a positive charge, chloride with a negative charge. And when they break up, these ions are also called solutes. So now in this, if you look at this, in this 75 ml solution, 50 ml was water. Okay, so that 66% is water, and 25 ml, 1/3. 25 ml or it was the solutes, so that's about 33%. Got that? So water here is 66%, solutes was 33% in this solution. In 50 ml of the solution, all 50 ml was water. So water was 100%. Have you followed? Right? When you take these two, compare these two solutions, which has more water? Solution A or B? If I say this was A and this was B. A, because it has 100%, right? So what happens is that if there was a membrane which allowed water to pass through, you will find that water will diffuse from an area of higher concentration to an area of lower concentration. And we'll see that we'll do this again when we do cell and membrane transport. But I just want to show you how these ions, or what we call solutes, become important, because what they tend to do is they tend to draw water towards themselves. Yeah, I said the water diffuses from an area of higher concentration to an area of lower concentration. So whichever solution has more solutes will tend to draw water towards it. So this solution has more solutes compared to this one, which has none. So it is drawing water towards it. So any solution which has more solutes, so the more solutes we have, we say that solution is hypertonic. And any solution which has less solutes, we say that solution is hypotonic. And water moves from hypo to hypertonic. So this was hypo, this was hyper. So water moves from hypo to hypertonic. And I'll give you a good example by way which you can remember. You know, you take a dried bean, you've got these garbanzo beans and red beans which you have to soak in water. When you get them, they're really dry, right? So there's very little water inside, but they've been dehydrated, so they've got a lot of salts inside, so they've got solutes. When you put it in water, what happens? It swells. Why? Because they have the bean, or the garbanzo bean, or the red bean has drawn water towards it. So can you see it's going from that bowl of water, which is hypotonic, into this bean, which is hypertonic, and that's why it's swollen. Okay? So fluid or water moves from hypotonic towards hypertonic. Okay? And we will do this again in cell transport, but this was just an introduction.
It's like a sponge, right?
It's like a sponge, yeah. You know, like how a sponge draws in water. Yes, yes. The next type of bond. So in ionic bond, which we just did, we said that, you know, you gave away electrons or you received electrons. But how about here a little bit of, a little selfishness. Like I don't want to give away, and neither do I want to receive all. I just want to share. So not selfishness, maybe they're better. So let's look at this situation here where we have a carbon atom and we've got hydrogen atoms. So carbon atom has 2 in the first orbital and it's got 4 electrons in the second one. So it needs 4 in order to become stable. Hydrogen has only 1 electron, right? So each of these 4 hydrogen atoms need 1 more in order to become stable. So can you see if carbon reacted with 4 hydrogen atoms, at each point it shared over here. So you can see the hydrogen will get 2 and the carbon will get 5. Now it shared with this one, hydrogen gets 2, so now it's got 6. It shared with this one, hydrogen's got 2 and now carbon has got 7. And it shared with this one, so hydrogen has 2 and carbon has got its 8. So it shares it with 4 hydrogen atoms and you get a gas which is known as methane. So you can see that because only 1 electron is being shared with each of the hydrogen atoms, you show the bond as just a single line. Can you see that over here? Okay. So this kind of a bond is this type of a covalent bond. Only 1 electron is being shared. Let's look at another example where let's take 2 oxygen atoms and you end up forming an oxygen molecule. So oxygen has 2 in the first orbital and it's got 6 electrons in the second orbital. So it needs 2. So if you got 2 oxygen atoms, if these atoms shared 2 of these electrons, they both would get 8, right? So they've got 6 and they're sharing, so 8. So you get now an oxygen molecule because 2 of the electrons were shared. You will show it as 2 bonds. So O, and you will write it as, if it's not clear, you will do this way, right? So just to show you that 2 electrons are being shared. In this third one, we are looking at nitrogen. So it's got 5 electrons in its outer orbital. So it needs 3 to make 8. So if it shares 3 with another nitrogen atom, you will get a molecule of nitrogen, and 3 electrons are shared. So each one of them will get 8. So you'll see nitrogen with 3 bonds. Can you see this? 3 electrons being shared. So this is covalent. This is called covalent bonding, where instead of giving one or taking one, you're actually sharing the electrons. Okay? So let's review this.
Is that one? I'm sorry.
Yeah. Yeah, go ahead.
This here, the nitrogen, you're sharing 3, so would that have 3 lines?
Yeah, 3 lines. This is not, it does not, there are 3. It's a little white, yeah. There are 3. Yeah.
Just one.
Yeah, no, you're not. The lines are not showing very clearly. Yeah. There are 3. Okay? So let's review the ionic and
Ionic
covalent
bonding
bond.
occurs between 2 atoms when one of the atoms has sufficient strength of attraction to remove an electron from the other atom. A sodium atom has 1 valence electron, with a stable energy level below containing 8 electrons. A chlorine atom has 7 valence electrons. If the atoms collide with sufficient energy, the chlorine atom will remove the electron from the sodium. The sodium atom loses its only valence electron and becomes a positively charged sodium ion. The energy level below now provides sodium with its stable octet. The extra electron completes a stable octet for chlorine, which becomes a negatively charged chloride ion. Covalent bonding occurs when neither atom has sufficient strength to completely remove the other atom's electrons. The atoms share electrons, and both atoms achieve a stable outer energy level. A hydrogen atom with 1 valence electron needs 1 additional electron to complete the first energy level. An oxygen atom has 6 valence electrons and needs 2 additional electrons to complete the second energy level. As the oxygen and hydrogen atoms collide, covalent bonding is accomplished by the sharing of electrons. By sharing an electron pair with the oxygen, the hydrogen completes the noble gas configuration of helium. By sharing with the hydrogen atom, the oxygen atom now has 7 electrons in its energy level, still 1 short of the stable octet condition. A stable octet for oxygen can be completed by sharing an electron with another hydrogen atom.
So you can see that's how water is formed. Okay? Now think of this question. When 1 atom of carbon combines with 4 atoms of hydrogen, how would you write the formula? And if you were looking at that slide that I showed you, the formula was actually written over there. Yes, it's CH4. You'll write it as CH4 and none of the others, not 4HC or 1C and 4H or not C4H. It's written as CH4 to say that there's 1 atom of carbon and 4 atoms of hydrogen. Okay? Now, when we looked at covalent bonding, we also have a different type of covalent bonding called polar and non-polar covalent bonding. non-polar covalent bonding is where the electrons are shared equally. That means it doesn't tend to kind of reside or sort of show preference for any one of the elements present. So one good example was carbon dioxide, where the two electrons between oxygen and carbon are shared equally on either side. So this is called a non-polar covalent bond. In a polar covalent bond, the bonding is done in such a manner that one part of this over here, where the two elements are interacting with each other in this molecule, one part of it tends to attract the electrons more and the other parts not so much. So the part which attracts the electrons more will be negatively charged, and the part which attracts the electrons less will be positively charged. Because remember, electrons have a negative charge. So anything, wherever the electrons go, it will carry a negative charge with it. So if you look at water molecule, it just so happens that you saw in that little video just now how oxygen had to combine with two hydrogen atoms to form water, right? Now it so happens that oxygen tends to have more affinity for the electrons. So the electrons kind of reside a little bit closer. It's like they favor the oxygen more. So the oxygen end of this molecule is negatively charged, and the hydrogen end of the molecule is positively charged. Okay, so it's like they have two separate poles, one negative pole and one positive pole. So that's why these are known as polar compounds. Okay, so water is one such example. And let's look at this in.
Water has a polar covalent bond, and water is one atom of oxygen, and oxygen has 6 electrons, 6 valence electrons, 8 electrons total, and hydrogen each has 1 electron. They share those electrons, but they share the electrons unequally.
I'm sorry, it's at the loudest. It's there in your notes too. So if you are not able to hear it, it's at the loudest, and unfortunately nothing else will work from here. Okay, so it's there in your notes as well.
So when the molecule bonds, when the atoms bond up, one side of the water molecule becomes negative, and one side of the water molecule becomes positive. The hydrogen sides are positive, the oxygen side is negative. Because of this, water is polar, and that gives rise to many of water's interesting properties that make water so useful. This bond right here is the bond between hydrogens and oxygens is called a polar bond. Make this a little bigger there. Polar bond. And the bond between different water molecules, so water molecules stick to each other because one side is negative, one side is positive, they'll stick. And the sticking isn't as strong as the bond between hydrogen and oxygen. It's a pretty weak bond, but this bond is called hydrogen bond. And these bonds are constantly forming and breaking, and they lead to water's many amazing properties, which we'll discuss next.
So he just showed you polar bonds and was saying the same thing, how one end of the molecule is more positively charged and the other end was negatively charged. So with the result, we also get what is the formation of weak bonds, which are known as hydrogen bonds. And water molecules are the best example of this, where you see that hydrogen, which is positively charged over here, you know, if you put droplets of water, they tend to kind of stick to each other. That's what gives rise to surface tension of water molecules. So if you put water molecules together, they will stick because the hydrogen, the positive end of one will react with the negative end of the other. So they pull each other like this, and that's how water molecules can stick to each other. But these are weak, but they can also be broken, so you can, you know, break them. Yes? Yes, it is, but here when you get a polar bond, what happens is that electron which it is sharing, it tends to reside more towards the oxygen side and less towards the hydrogen. So that's why it's relative. So that's why we say that end is more positively charged as compared to this end, which is more negatively charged. It's not equally shared like we saw in carbon dioxide. That's why we say that that part is positive. It's not that the electron has disappeared or anything. It's just that the electron resides more towards it. And think of it as color. There's more color towards this end and less towards that end. So like that, okay? So that's why that's why we say it's a polar bond. We don't say the whole atom is negatively charged or positive, okay? Now let's look at something called chemical reactions. And the first one is where you're actually making something. So when you make something, you use energy, and usually water is released. So imagine if you have to build a house, you're going to use energy, right? So and you start with small things like small bricks, and then you make a big house. Similarly, in your body, when you from small substances you make large substances. This is usually how it happens. So you're synthesizing something. Synthesis means to make. This is known as a synthesis reaction, or also known as an anabolic reaction. An anabolic is when something is made. One example is when many amino acids join together to form proteins, or very small molecules, simple sugars join together to form complex sugars, like glucose joins together to form glycogen. So that's another example. Or fatty acids and glycerol join together, many of them, and then will form a big lipid. So these are synthesis reactions, okay? These are known as anabolic, and when anabolic reactions come about, water is usually released. The opposite of this is decomposition reactions or catabolic reactions. What happens when you need less energy to break down a house than to make one, right? So usually energy is released, water is used. So these kind of reactions are often known as hydrolysis reactions. So a good example is that in your I told you when many glucose molecules join together, they form glycogen. Glucose is a simple sugar, glycogen is a complex sugar. So joining glucose together to form glycogen is an example of an anabolic reaction. Look at the opposite. When glycogen is broken down, it will give rise to many glucose molecules. And so this is decomposition, you're breaking down. So it is known as catabolic, and water is often used to bring about this reaction. And one of the questions you got in the quiz was, you know, when glycogen is broken down to make glucose. I think there was a question like that. This usually happens because when you eat glucose, when you eat sugar, what happens, your body uses the glucose, and whatever extra glucose is there, most of it goes and gets stored in the liver and skeletal muscle as glycogen. So the glucose molecules join up together and form this big complex called glycogen, and they store it. Then when your body needs it, let's say you haven't eaten for a while and you need energy, it will bring that glycogen from the liver and skeletal muscle, break it down, provide glucose as fuel for your cells, and that glucose then gets broken down into ATP, which you can finally use. Because ATP is the utilizable form of energy for your cell. You can't use just glucose. You have to break glucose down into ATP to be used, okay? So this breaking down glycogen, which is a complex molecule, into simpler molecules is an example of decomposition, or what is known as catabolic reaction. Next type is exchange, and this is very simple, where you're kind of exchanging the elements. So let's look at this one where hydrochloric acid and sodium hydroxide are reacting. So you get hydrochloric acid, the hydrogen reacts with the oxygen, hydrogen forming water, and the sodium reacts with the chlorine. So you can see, like if you had AB plus CD, you get AC plus BD, you know. So this is where the elements are kind of exchanged between each other. And here is a reaction which we have where this is the symbol for glucose, and this occurs inside the cell, how ATP is manufactured from glucose. I just told you that you can't actually just use glucose. because, people who have diabetes, they have a lot of glucose in their bloodstream. The problem is that glucose cannot get into their cell because of a lack of a hormone called insulin. And once the glucose actually gets inside the cell, it actually has to break down and form ATP. And ATP is the energy molecule that the body uses for all its activities. So this is what happens inside your cell. So you get glucose combining with oxygen, which is why oxygen is so important for us. And you break it down into carbon dioxide, which we breathe out, water, and ATP. So that ATP is what is stored inside your cells, and when the body needs, then it calls upon it to, carry out its functions. So here you can see that it's catabolic because there is breakdown of the sugar. There is some synthesis going on here because here you are synthesizing ATP. So you can see this kind of reaction, mainly catabolic, some amount of synthesis because you're synthesizing ATP. Some chemical reactions in the body are reversible. That means they can go either way. So based on what the body needs. One very, very common example is the formation of something known as carbonic acid in the body. And this occurs inside the red blood cell, in the plasma. It's very important for respiration. So water is always present. Most of your body is made up of water. And you can see where the water is coming from, apart from whatever you drink, even with cellular mechanism like breakdown of glucose liberates water. So in your red cell, for example, water combines with carbon dioxide and it produces this weak acid called carbonic acid. When the body needs, this carbonic acid can actually break down or go in the reverse direction and be broken down into carbon dioxide and water. So this is kind of reversible. So depending on which way the body needs the reaction to go, the reaction will go in that fashion. So when you do respiration and so on in ANP2, you will again come back to this reaction and you'll see how it is used. Okay? So let's look at this. When you eat a piece of chicken, it's broken down in the digestive system by enzymes to form amino acids. What is this an example of? This is an example of a catabolic reaction. Remember right in the beginning, the first one, when I said synthesis, I said amino acids, you join amino acids together to form proteins. So here when you eat chicken, chicken is protein. You're actually breaking down, the word breaking down should have given you the hint. You're breaking down a complex protein into smaller amino acids. So this is a catabolic reaction, okay? Now here are some factors which influence chemical reactions. Temperatures, usually higher temperatures tend to speed up chemical reactions, higher temperatures to an optimal level, which is why in your body, for example, you need to maintain your body temperature. If your body temperature gets too high, then enzymes can get denatured. If your body temperature gets too low, you know that all metabolic activities kind of stop, right? So you need an optimal temperature. So raising the temperature to a certain level speeds up the action. Particle size, the smaller the particles are, the faster they are able to react. They're able to move about much faster. So smaller particles react much faster. Concentration, the more there is of the elements which have to react, so the more concentrated a concentration there is of the elements that are reacting, the quicker and faster the reaction will be. If you have less of the elements, obviously the reaction is not going to be that much. And then in the body you have certain catalysts which kind of speed up the reaction. These catalysts are called enzymes. So they help to kind of speed up without getting changed themselves. So they don't take part in that. They don't get chemically changed during the reaction. They only help. So think of them as moderators. Two people are having a fight and you as a moderator kind of, say, do this, don't do that. So you don't kind of get changed. Those people do their job, okay? So not a great example, but that's the best I could think of.
Instigator?
Pardon?
Wouldn't it be an instigator?
yes, you could think of it that way too. That something that's bringing about a reaction. Yeah, I could say an instigator too probably would be a better example. Yeah. Okay.
Can you use catalysts and enzymes interchangeably, or are they two separate things?
Most of the time, enzymes are the ones which act as catalysts, but sometimes you may have some substances in the body which may act as a catalyst. We may get minimal change, but for purposes of this class, we'll use them
So
interchangeably.
enzymes don't change, catalysts do change.
Some of them, some, yeah.
Wait a minute, now I'm confused. What?
So that's why I said, for now, for our purposes of our class, we'll use enzymes as catalysts, and enzymes do not change in a reaction. Let's look now at biochemistry. So we look at inorganic compounds first. Water, which forms about almost 80% of all your living cells. It's inside your cytoplasm. It is the solution in which all the other substances are dissolved. So we call water a solvent. Solvent is something in which solutes are dissolved. It's a very good transport medium. So you can see plasma is 55% water. Gases are transported in plasma, vitamins, nutrients, everything. So again, it's a good transport medium used in reactions where you need to break down compounds. So that is the hydrolysis reactions I was talking about. In certain parts of our body, like we did serous cavities, if you remember, the pleural, pericardial, and peritoneal, these contained small amounts of fluid, of which it's mainly water. They act as a lubricant. In your synovial cavities of your joints, again, you have this lubricant. So it acts as a lubricant in many areas of your body. Protective in function, through its lubricating function, it's very protective. So it has a very, very important role to play. So while it is a solvent, dissolved in water are many substances. Of them, we have salts. Sodium chloride is one, potassium chloride, calcium chloride. These are all salts. They break down into or dissociate into ions. Like you got sodium chloride, positively charged sodium, negatively charged chlorine. Potassium chloride, positively charged potassium, negatively charged chlorine. So this way, okay? So they break into ions, and ions are capable of allowing electricity to pass through. So we call ions electrolytes. So whenever in your, if you've ever looked at, next time you buy a bottle of Gatorade or any of these sports drinks, just look at the electrolytes listed there. So the electrolytes would be sodium, potassium, chlorine, bicarbonate, all of these which are charged. So these are all your electrolytes which are very important. They are present in your cell. Calcium, they're present outside the cell. Sodium, all of these. So these are electrolytes, very, very important.
And they allow electricity to pass through. And
Yes.
That's what makes them.
No, they are charged particles, which is why they allow electricity to pass through. Then we have acids and bases. Acids are substances which release hydrogen ions, and bases are substances which mop up hydrogen ions. So if you look up here, hydrochloric acid, hydrogen ion, and chlorine. Bases, sodium, NaOH is sodium hydroxide. It releases sodium and a hydroxyl ion. This hydroxyl ion then actually mops up a hydrogen ion to form water. So you can see how bases will mop up hydrogen ions, whereas acids release hydrogen ions. An important base is something known as bicarbonate. HCO3 is a bicarbonate. It's a very, very important base in our body because it takes part in something known as it acts as what is known as a buffer. And before I come to buffer, let me tell you first, why do you need a buffer? In your body, your blood pH is maintained at something known as something between 7.35 and 7.45, the pH of your blood. And you always want to keep it constant at that level. So what is pH? pH is the amount, the number of free hydrogen ions. So the more hydrogen ions you have, free, the more free hydrogen ions you have in your body, we will say that your pH is acidic, but the pH number is low. That means from 0 to 7. This is what is acidic. Okay? So if you have, say, 100 hydrogen ions, I'm just saying, suppose you have 100 free hydrogen ions, your pH is 5. If you have 150 free hydrogen ions, your pH is 3. Do you understand? The higher the number of free hydrogen ions, the lower the pH number, the more acidic it is. Right? The more acidic it is means numerically the number is low. Lower the number of hydrogen ions, the more basic or alkaline your pH, which means that the higher pH number. So between 7, from 7 upwards, let's say 7 to 14, we say this is basic or alkaline. So if I had, say, 75 hydrogen ions, free hydrogen ions, let me say my pH was 8. And if I had 50 hydrogen ions, my pH would be 9. Do you understand? The lower the number of hydrogen ions, the more alkaline the solution is. And the more alkaline the solution, the higher the number, the numerical value. Okay? Have you followed? The more the hydrogen ions, the more acidic your solution, but numerically your value is lower. Okay? What do you say? If I ask you which solution is more acidic, 2 or 3? 2, right? So that means it has more hydrogen ions. So think of it like that. Now, buffers are solutions or substances in the body which resist a change in the pH. So what they do is, if your pH goes either below 7.35 or above 7.45, depending on what happens, what the buffers will do is they will either release hydrogen ions to bring down the pH, or they will mop up hydrogen ions to take the pH up. Got that? So buffers, they prevent the pH from changing. They like to keep it in the range. So they either release hydrogen ions or they mop up hydrogen ions to make sure that the free hydrogen ions which are floating, they are not increasing or decreasing in number. One very good example of buffers is this bicarbonate, this thing called carbonic acid. This here is called carbonic acid. And this is bicarbonate. So it's often called the carbonic acid bicarbonate system. So it's often called the carbonic acid bicarbonate system. And you can see how carbonic acid can release hydrogen ions if needed. Or if there's bicarbonate, it can mop up hydrogen ions. So can you see how both can act as buffers? So you can either release or you can mop up. Okay? So let's look at this question quickly. A solution of pH of 4 will be? Yes, it will be acidic. Let's look at organic compounds. So we have carbohydrates. These are the best sources of cellular fuel. Glucose, whenever your body wants quick cellular fuel, glucose is the first thing it looks for. And carbohydrates are in 3 categories. The simplest are called monosaccharides. The second is called disaccharides, and the complex carbohydrates are called polysaccharides. And this picture here kind of shows you the monosaccharides: glucose, fructose, galactose, deoxyribose, ribose. They all contain carbon, hydrogen, and oxygen. And here you can see when glucose and fructose join together, they form sucrose. So this is a synthesis reaction. When sucrose is broken down, it forms glucose and fructose. When just 2 glucose molecules join, they form maltose. When galactose and glucose join, they form lactose. So these are disaccharides. And glycogen and starch are examples of polysaccharides. Glycogen and starch are examples of polysaccharides. Lipids, These are nonpolar compounds. Triglycerides are, they contain 3 fatty acids and 3 fatty acids plus glycerol, triglycerides. They are very efficient fuel source because for a single gram you produce much more energy than you would do with glucose, but you don't always want to have too much fat in your body. The fat is deposited in various areas of the body where protection is needed, for example, around organs, under the skin, where subcutaneous tissue, around blood vessels. Three fatty acids plus 1 molecule of glycerol, so that's what a triglyceride is. Fats can be seen in various important parts, important substances in your body like hormones. Steroid hormones contain fats. The cell membrane is phospholipid in nature, so that again contains fat. So, you can't totally be on a fat-free diet because your body does need fat. And amongst the fat, there is good and bad. There's one kind of fat called saturated fat, which has single covalent bonds. And this tends to be solid at room temperature because it can be straight and the molecules can get tight and adhere to each other. The unsaturated fats have double covalent bonds. They may be either 1 or 2 covalent bonds. You've heard of monounsaturated and polyunsaturated fatty acids. Why are they good? Because these do not they are liquid at room temperature. They don't solidify. And that's because their bonds are such that they kink, so they don't allow them to kind of adhere to each other. So that's why they don't sort of coalesce and become solid. Proteins contain nitrogen and sulfur. Apart from the carbon, hydrogen, and oxygen, they have nitrogen and sulfur. They are very important building blocks of our body. They're seen as the simplest form of proteins. The building blocks are known as amino acids. Many amino acids combine and they form peptide bonds. And when you have about, 10 or more peptide bonds, you call it a polypeptide. And when you have more than 50 of these amino acids, you call it a protein. Proteins are important because they can get heat. Very, very high temperature can denature the proteins. So that's why very high temperatures are not good for your body. You always want to bring down the temperature. When it goes beyond 103 or something, you're always worried because body systems stop functioning. Okay. We still have a few, let me just see how much is. Okay, I think we'll stop.